Yeah. Things are being recorded. Be careful what you're saying. No. All right. So let's start then with a kind of recap of what we did. Sorry, my voice is failing. So yeah, this is like some comments on what we did last lecture. Comments on Riemann von Mangoldt formula. I mean, explicit formula. There are two things I will tell you. Explicit formula. So first of all, what was the formula? The formula said that sum lambda of x, well, actually lambda of n, rather, n less than equal to x. Yep. N less than equal to x is equal to x minus sum x rho over rho, summation over rho, minus 1/2 log of 1 minus 1 over x squared, minus zeta prime of 0 over zeta 0. Yeah. So this was the formula that I gave a sketch of the proof. It was not, but there are some details I will tell you that still has to be worked out, but the sketch is there and the ideas are totally there. So first of all, the first comment is something we discussed. Zeta of 0, you already know what it is. You calculated in your assignment. Zeta of 0 is minus 1/2. And zeta prime of 0, I didn't ask you to compute it. It's a much harder calculation, but that's also known. That's equal to, minus log. It's over there, actually, minus log root 2 pi. So this factor is really like log 2 pi. The whole thing is log 2 pi. So this is like just minus log 2 pi. Okay, so that's a constant in the formula. And the second thing is that there is this thing called this function. If you introduce the function psi x equal to sum lambda n less than equal to x, this is called Chebyshev function. It was introduced by Chebyshev. Chebyshev psi function. So Chebyshev called it, I believe Chebyshev called it psi, and it's forever, it's called psi function. So that's a function introduced by Chebyshev. Because Chebyshev proved a weak form of the prime number theorem, a kind of estimate an inequality between, he put pi of x between two limits. He didn't prove that the limit is asymptotic to x over log x. He said that it's between two things which are related to that. So yeah, okay. So I mean, this function is equal to as we define is sum log p over all t to the k less than equal to x. So this is, if you want, is a summation over. This summation is over pairs of primes and integers k such that p to the k is less than equal to x. It's a finite sum. It's just that one. So this is an example of a prime counting function. Is a prime counting function. So there are many prime counting functions. The most famous is the original one that we have, like pi of x. Another one is pi of x, which is just sum 1 p less than equal to x. All primes summation is over a set of all primes that's less than equal to x. So this is equal to number of primes, p, less than equal to x. That's what it is, yeah? Yeah, but the thing is that the reason we call it prime counting function is that they can all be expressed in terms of each other. So if you know one of them, you can compute the other one. They can be expressed in terms of each other. They're like Fourier transform related to each other. Yeah, and this is a big kind of business in prime number theory to relate those things. So now prime number theorem, of course, is equivalent to, but we will see a quick proof in Mac's presentation. Prime number theorem, it just says that pi of x is asymptotic to x log x. And this is also asymptotic to Lie x. You remember the formula for Lie x? Anyone remember the formula for Lie x? Yeah. Yep, someone. Integral 2 to the x, not the x, the t. dt over log t. Yes, that's from the first lecture. So this is, now it can be shown that actually this prime number theorem is equivalent to a statement about psi. And that's the relation between psi and pi. So PNT is equivalent to psi of x is asymptotic to x. You see, here, this is like a leading term, and these terms are comparatively unimportant compared to this one. I mean, for this is of course obvious, because as x goes to infinity, this goes to log 1. This is diminishes fast. This is what? 0. And this is also constant. So compared to x, doesn't play a role. But the problem is here, is the second term, which is just has to be dealt with. And that's the difficulty of proving prime number theorem. But anyhow, the statement of the prime number theorem, if you want, can be formulated in terms of psi function or in terms of pi function. And in fact, there are 2, 3 other counting functions. They can be expressed in terms of all of those. 2 of them, it belongs to Chebyshev, but yeah, and there is 1 or 2 that belongs to Riemann, actually. So I will maybe mention those. Okay. So this is the second comment I wanted to make. And now the third comment is that the summation that goes there is over, yeah, non-trivial zeros of zeta, right? Why can't we buy one of these things? Yeah, I can. Yeah, this is so strange. Yeah, maybe that's better. Okay, good. Yeah, so in x over rho, summation is over. Non-trivial zeros of zeta. Zeros of zeta. In other words, they have to be, the real part has to be between 1 and 0, including 1 and 0, though, because we don't know if there are no zeros on the line, real part of rho equal to 1 or 0 yet. But let me write it down so that you can see. So here is the picture. You should bear in mind. This is 1, this is 0, and all non-trivial zeros are here. And a priori, this line and this line are also included in the formula. Potentially, they're included. They're there as well. But what's going to happen is that actually, what happened is that Hadamard showed, and de la Vallée-Poussin as well, de la Vallée-Poussin, showed that there are no zeros on the real line s equal to 1, on real part of s equal to 1. You see? So and now I claim that there are no zeros on the line real part of s equal to 0. Why? And no zeros on y? Sorry? What is the functional equation? Capital Z, yeah, exactly, yeah. From that, it follows that no zeros on real part of S equal to 0. But that's something that that's a hard theorem. That's more or less is equivalent to prime number theorem using this von Mangoldt formula. So the strategy for these two guys was to use von Mangold's theorem plus proving that there are no zeros here, and then a little bit of crafty work with that thing, with that expression. They could show that actually contributions here are not as strong as X. They're much smaller than this one. So that's it. Another thing is about the summability of this series. I was going to mention yesterday, the series is only conditionally convergent. That's very important. So this is the still third point. Yeah. Sum x rho over rho is conditionally convergent. It's not absolutely convergent. It's conditionally convergent. In the sense that this limit as t goes to infinity, sum, x rho over rho, where imaginary part of rho is less than t, absolute value of imaginary part of rho is less than t, this converges. It's convergent as t goes to infinity. So this limit exists. But if you try to sum it as an absolutely convergent, it is not absolutely convergent. And that's a big problem, actually. I mean, difficulty for estimating these things, not getting information about primes from this. That's another thing. Okay. So, and in fact, this sort of came up in our proof because we took contours which went from minus t to t and then extended the contour. So this was kind of, So, any questions or comments? It's convergent. Yeah, if something you cannot read, absolutely ask. Yeah, I wrote it quite fast. Yeah. Any other questions? Okay. So that's about that. Now, what else I wanted to comment here? Yeah. So there is a variant of this thing, which is called truncated explicit formula. in a way, is kind of more useful than the explicit formula that I wrote over there. So let me write it here. So this is 0.4. There exists a truncated. So instead of taking infinite sum, we just take finite sums. There exists a truncated Riemann von Mangoldt formula. So it says that indeed sum lambda n less than equal to x is equal to x minus some x rho over rho, absolute value of gamma. I mean, yeah, imaginary part of rho, let me put it less than equal to x. Summation is over only finite number of rows now, finite number of zeros. Plus, those other terms, you can just estimate it to be O of log squared of x. I'm not sure if Hadamard used this truncated version or this version. But this is also very useful because it's a finite sum here. There are finite remaining. Yeah, this definitely we know without knowing anything, just complex analysis, because it's a compact set and you have a non-zero function, which is zeta. So the set of zeros is discrete. So it's going to be finite in any compact set. So if you just look at in this kind of domain, in the compact things, then the set of zeros is just discrete. This much we know. Okay, now, so, right, rho is equal to, for example, something like beta plus I gamma. Then if you study what is x rho, is x to the power beta plus I gamma. So if you want to estimate the absolute values, this is going to be equal to x to the power beta. But beta is, of course, real part of your zero. Now, here is the idea that, so we know that prime number theorem is the statement that, well, this is psi of x, by the way, of course, is the statement that psi of x is asymptotic to x. But now the question is, what is the remainder, right? You want to know what the remainder is, plus some remainder. Okay, the remainder seems to be the smallest possible remainder if Riemann hypothesis is true. So that's the one reason why maybe Riemann came across this. I don't know, but now if it happens that beta, which is equal to real part of rho, is equal to half for all rows, non-trivial zeros, then this truncated formula star implies that actually we have the form of this thing. We have psi of x equal to x plus O of root x log squared of x. Here, these terms are all of the form x to the power half here, if all the roots are of that order. But otherwise, let's see what happens if that's not the case. Otherwise, because we know that the roots come in quadruples, right? The roots come in quadruples. Since roots come in quadruples, so these roots come like this. If rho is a root, in other words, 1 minus rho is a root as well. And then rho bar also is a root down there, whatever. And 1 minus rho bar. So if you have a root with real part of S less than half, then you're going to have a root with real part of S bigger than half. So this is going to spoil this. You get a larger estimate here rather than root x. The remainder is going to be bigger than what this sort of ideal remainder you can guess. So this seems to be the best scenario because of the symmetry. That's not. So so let me write it. If there are roots with beta bigger than half, or equivalently, beta less than half, or equivalently beta less than half, then we conclude that, then we can conclude that at most what you can say, psi of x, you can say is going to be equal to x plus O of x to the power 1/2 plus epsilon for some epsilon positive. Because root x is bigger than log squared of x anyhow. So, but here, this root x, you cannot do anything. So you have to accommodate for that extra factor here. So this is the best you can do. And this is a much bigger number than that one. Because here, again, you have root x to the power epsilon. This is bigger than log squared of x. You cannot do better than that, yeah. So maybe that's why Riemann thought that if beta, yeah. So I think the statements that he writes is that many zeros are on the critical line, and it's likely that all zeros are on the critical line. He had calculated some zeros, and this is a heroic calculation that there's no way I can tell you, and people didn't know his calculations, so it was hidden in Göttingen archive, and then a great mathematician, 1932, Siegel, was searching, and he just found formulas in his documents, and it's very hard to decipher the way he wrote. Everything he wrote is correct, but it's very, very hard because they're all handwritten and scattered, and they're just very, very unorganized, disorganized. Before Siegel, nobody could make any sense of those writings, but Siegel did, and then he really had zeros. So let me give you some zeros that actually was calculated by Riemann, and then we move on. Any questions, by the way, or comments? Yeah. Yes.
Even about you then it goes like this. If someone could the converse would either be they show that growth.
I believe so. Yeah, that's a good question. I believe so. Yeah. Yeah, I believe so. Although, I mean, don't quote me on that. I'm not. I believe I have seen a statement that this is equivalent to Riemann hypothesis, but these things can be checked easily.
Yeah.
Any other questions or comments? No? Okay. So before I give you something about zeros, let me tell you another great result that was this time it was stated by Riemann, but his proof was not complete, but he correctly stated it completely perfectly. So let me write it down. And this is the so-called the density of primes on the critical strip. And that's where relation to random matrix theory and this sort of things come into the game. So let me write it. So Riemann's formula for NT equal to number of zeros, density of zeros. Did I say density of primes? I should have said density of zeros. Density of zeros in imaginary zeros rho in imaginary part of rho less than t bigger than 0. And of course, real part of rho has to be between 1 and 0. So this is the quantity that you were worried maybe it is infinite, right? This n of t could be, you said, do we know that this is finite? And I told you why this is finite. So you just look at, there may be some zeros here. Hopefully not off the line. And hopefully these are bigger than 10 billions. I think anyhow, so you go up to t. Okay, so this is the thing. And the question is, how many zeros are there between 0 to t? And let's call that number n of t. So this is like prime counting function, but this time is for zero counting function. We are counting number of zero because the two things are related and we want to know, we want to have a good estimate for that as well. So Riemann gives a formula for this. So Riemann's formula is that n of t is equal to t over 2 pi, I believe, log of t. Is it over 2 pi or just t over pi? Or just t? I'm not sure. Oh, it's 2 pi. Yeah, it's all the way 2 pi. Yeah, it's just, yeah, okay. Over 2 pi, then minus t over 2 pi plus O of log t. As t goes to infinity. So what does this mean? First of all, you know what this statement means? It means that if you bring these two terms to the left-hand side and take their difference, plus rather t over 2 pi is less than equal to c, some constant, times log t for some constant c. Hmm? Yeah. So what does it say about the density of primes? Now, the density of primes, of course, right? This is, of course, is nt divided by t, right? And this is just log of t over 2 pi. That's all. Because this drops. When this is a constant, it doesn't matter. As t goes to infinity, the density of primes is asymptotic to t over 2 pi. Oh, no, sorry, log t over 2 pi. Oh, 1 over 2 pi, rather, log t over 2 pi, as t goes to infinity. So this result, which was written down by Riemann, shows that not only there are many primes, in fact, their density is increasing. As you go up the scale in the imaginary axis, the density is actually increasing. There are more and more zeros as you go up the ladder. Yes.
Density of primes because this relation.
Density of zeros, I said. Oh, zeros. Sorry. Yeah.
How we use the.
No. This is a different thing, and I'll give you how it is proved. Actually, I'll give you the proof. And of course, you remember the density of primes, right? What was the density of primes? You remember? So what is density of prime? Basically, on the average, how many primes exist between in the interval 0 to x? That's what it is. Like pi of x over x. And this is asymptotic to what? 1 over log x. Not log x. It's 1 over log x. Because the guy itself is pi of x is asymptotic to x over log x. You divide it. And you get. So what does it mean? It means that actually primes gets thinner and thinner in a way. The density is decreasing, but the density of zeros are increasing. Anyhow, so this is what it is. So it's not, Riemann gives 1 paragraph or maybe 2 paragraphs reasoning for this. His arguments, nobody knows. People believe that his arguments are not correct, but nobody knows how he came across the exact formula, because this formula was proved later on. So this is a star proved. Yes, by whom? Yes, by whom? No. Ramanujan never proved anything. He had everything right, but never proved. I'm sure. No. The guy who already proved something big, von Mangoldt. So this was proved by von Mangoldt. Again. So we owe to von Mangoldt 2 things. First of all, the explicit formula. He understood Riemann really very well, it seems. He scrambled the explicit formula into a form that's better even, more usable, and he proved it. His proof is correct. And he also proved this statement. So this is called now Riemann von Mangoldt formula in honor of von Mangold's contribution. Okay, so now let me give you an idea how this is done. Because this is, again, complex analysis. It's nice complex analysis. I just give you a sketch. I mean, I don't give the proof because it just, people give these things. I mean, takes 1 term to talk about this thing. But that's okay. But it's good to know the proof. So how do you find how many zeros a holomorphic function has? Do you remember a result from complex analysis? Huh? What is the result that you use to estimate and actually get the exact number of zeros and poles of a meromorphic function? Huh? No, it has a name. Huh? What's that? It's the argument principle. Yes, exactly. It's called argument principle, and so proof is based on argument principle. So what is argument principle? Well, argument principle says that assume F is meromorphic. So some open domain in the complex plane to C is meromorphic and holomorphic on the contour, holomorphic on C. So this is a contour that I take it counterclockwise oriented and a simple closed contour. So the function has some zeros and some poles. So I denote poles by negative charges and zeros by positive charges. Okay, so imagine there are like, so then the formula says that, so this is your curve. So the formula is that integral f prime z over f of z dz, 1 over 2 pi I over c is equal to z minus p. Well, z is the total number of poles. But we have to be careful. If you have a pole of order 2, zeros, sorry, zeros, yes. You have to be careful. If you have 0 of order 2, you have to count twice. So this is counting multiplicities, and this is number of poles. And you know how to prove this, right? Count the order of the pole, yeah. If you have a pole of order 5, it counts 5 times, but then negative 5. Yeah. Yeah, if you don't know, you have to think about how to prove it, but that's important. Already yesterday we discussed some idea which was quite related to that. Anyhow, so you use this, so then apply this. The function. So there is one function which is called xi of s, which is 1/2 s 1 minus s times z of s. So in other words, this is 1/2 s 1 minus s pi to the power minus s over 2 gamma of s over 2. Yes, zeta. Now I have to be careful. Zeta of s. This function xi of s. Now, this function, why did I multiply by s and 1 minus s? Well, I mean, one possible reason or plausible reason, maybe you can tell me why. Exactly. We want to kill the poles because z of s has 2 simple poles at 0 and 1, right? So we want to kill those. So as a result, this function is actually a holomorphic function in the complex plane. So it's an entire function. I don't know if you know this term or not, you were told in complex analysis or not, but this is an entire function. Why did I multiply by 1/2? I give $5 to person who can tell me why do I multiply by 1/2. I give $10. $20. $50. I'm serious. $100. The reason is that Riemann put it 1/2 and nobody knows why, and everybody repeats. Everybody's just afraid of changing Riemann's notation. So that's the power of austerity. So this was invented by Riemann. Yeah. Riemann said so. And nobody knows why he put 1/2 there, really. I mean, but everybody is afraid changing the notation, changing the 1/2, and it would work, of course. Nothing would change. I mean, maybe it's even better. I don't know, because there are sometimes people introduce constants that it makes things easier to work with. That there is some rationale behind introducing those constants. You know, for example, in physics, the force is minus gradient of the potential, not gradient of the potential. And that's a very convenient thing to have. But in mathematics, we always work with gradient of the potential, but in physics, never they do that. But there's a very good reason, because when you do that, then the law of conservation of energy becomes kinetic plus potential energy is constant. Otherwise, you have to say that kinetic minus potential energy is constant, which would be kind of funny, because you want to sum of the two things is constant, not the difference. That would be true still with the other convention, but nobody knows why this 1/2 is there. So you just keep it there anyhow. So that's why I guessed I was willing to waste $100. So possibly. Okay, so then you apply it to this function, and the domain that you have to get in this case is the following. So this is 2. That's irrelevant. This is -2, and there is it -2 really? Do I want -2 or -1/2? -1/2, yeah, up to -1/2 here. And here is 1/2. Yeah, so this is like 2 plus IT. This is -1/2 plus IT. And 2 minus IT, -1/2 minus IT. So, of course, zeros and this function has no poles, right? I mean, it's just zeros. And zeros of this is the same as zeros of zeta. So if you estimate using this, you estimated this one. And then, yeah, then there is some analysis of this expression. You have to derive the formula. It takes half an hour writing. I won't write it, so you can check. I'm just telling you that this exists, and this is really very important formula, really, to know the density of zeros of zeta on this critical strip. It's very important. Okay, so what else I wanted to say? More comments. No, I think we can just keep going, and then in 20 minutes we can finish. So I don't want to say more right now. Yeah. So I won't write the Riemann's form of the explicit formula. Well, maybe I just write it, because Riemann had a form of explicit formula in his paper. I just write it down so that you see how it is. Yeah. Yeah, right. Good. So let me write this. So this was 0.4. Yeah, question.
Side period?
Yes.
-1/2.
Oh, no, this is half. This is the critical line, of course. And this is -1.
Okay.
Yeah. Yeah, this is. Yeah. Yeah. So of course, this is the x-axis, but the y-axis is irrelevant here. This is the critical axis or line that matters as the vertical one. I mean, nothing is as important as the counter itself. So anyhow, but I'm just giving you some idea. I didn't prove it. I mean, but so one more thing from, yeah, so Riemann's explicit formula. So Riemann makes the following statement, that pi of x is equal to Li of x minus 1/2 Li of root x minus some Li of x to the power rho, summation over rho, plus W of x. Again, remember Li of x was this, of course, things that we know, 2 to the x, et over log t. And the prime number theorem is the statement that pi of x is asymptotic to Li of x. But he gives the exact formula. But W of x is a much smaller function compared to the others. This is smaller than the other three. So Riemann's proof of this is almost correct. I'm not sure, but maybe, but this has been proved. And this is also equivalent to Riemann von Mangoldt explicit formula. Yeah. Yeah, but I mean, you can extend this function to complex plane. That's not a problem. You can, because you just integrate, and this is a holomorphic function in a domain that you choose, and then that's okay. Yeah. Yeah, you can extend it. Yeah. Yeah, you have to worry about these things. Yeah. But that's in this case as well. And it really is independent of path of integration because this is a holomorphic function, and on its domain that's holomorphic. And in fact, it's much better to define function using integration rather than by ad hoc methods. Okay, I can tell you over the break. So this is the explicit formula in the sense of Riemann. So basically, you want to see? Yeah. So basically, we covered everything in Riemann's paper, so to speak, except one item. And that's the first item he touches. And that's his first proof of analytic continuation and functional equation. So I'm going to look at that now because that has a. So maybe a review of Riemann paper. I mean, review is really exaggeration. I should say, in quotation. I have to moderate my claim. Review of Riemann's 1859 paper. Okay, so first of all, it has two proofs of analytic continuation and functional equation, right? Okay, I mean, what is his first big idea? I started this series of lectures with that idea. What was his major first idea? Do you remember? What was that? Yeah, but what about zeta function? Because zeta was already known even by Euler. Euler used zeta function. Analytic continuation, yeah. He thought of zeta function as the variable s as complex. So zeta of s belonging to C. Second point was that he showed that it has analytic continuation. And functional equation, 2. So he gave two proofs of this, two proofs. I gave you his second proof. Now I'm going to give you his first proof today also, because it has some interesting new elements that would be good to know. So that was his second major advance in the paper. The third point was formula for n of t. Number of zeros of zeta of s in the critical strip, imaginary part of s. less than or equal to t, bigger than or equal to 0. Clear part of S less than or equal to 1, bigger than or equal to 0. And explicit formula, which is here. And even before these items, introduction of CS, which you lost the bet, couldn't make $100 for free today. 1/2 S, 1 minus S, Z minus S. I mean, he really did this, put this into good use in the paper. Roughly, these are the major points, but again, there are a lot of details there which have to really spend a lot of time exploring. So the last thing now, I want to, is that okay if I keep going for 15 more minutes and then we are done for today? Any questions, by the way? Oh, yeah.
0.
An actual 0. Yeah. Okay, right. Good point. Yes. I won't prove that. Actually, I won't produce a real 0 for you, but I give you the values of the proofs. So yeah. Okay. Yeah. This is so. Yeah, you can actually. The first proof, 0. I mean, is. I mean, okay. So what we are doing is we are looking at imaginary part of rho only in the upper half plane, because the thing in below is just conjugate, right? So we're just looking at it. And let's call it t. The first 0 as t equal to 14 point, I believe is 1. Actually, I wrote it somewhere. Must have it somewhere. I hope. What is it? Let's see. I'm sure I have it somewhere. Oh, yeah. Here it is. Yes. Last page. 14.134. Well, mind you, this has been calculated at least up to 1,000 digits. Okay, this has been done. The next one has t equal to, 21, I believe, 0.22. The next one is t equal to 25, 0.10. Next one is 30.0424, I believe, yeah. So 100 of them, you can check. There's a page belonging to this guy, Plouffe. Actually, he's Canadian. He's a virtuoso of these calculations. He gives the first 100 digits, each of them up to 1,000 decimal places. Calculus them. So the last one, the 100th one, is 236.524. So before the age of computers and new knowledge was new techniques, this was very hard. I believe, I mean, this one definitely was calculated by Riemann. Maybe this one also, maybe this one. I'm not sure. But the first few were calculated by Riemann himself. Sorry? No. They go on. They're not rational. I don't know. Because they have been calculated up to 1,000 decimal places. I don't know.
You don't know.
I don't know. And I'm not going to bet any money on that. If you want to get me into betting, again, I won't bet my money on that. Yeah.
How's the like,
Explicit?
yeah, like is it or is it how like where are these?
Good question. Riemann used actually a saddle point technique. It's a totally different. Yeah, he used saddle point. So yeah. He deformed. I will write the integration formula for zeta function, and he deformed the contour of the integration, and he used saddle point techniques, and then very, very actually sophisticated saddle point technique to calculate that. Yeah, that was Riemann's approach, which is quite hard.
Was Laplace's method known as that?
Oh, of course.
Oh,
Laplace
okay.
was 100 years, well, was 50 years before Riemann, yeah.
Oh, okay.
Yeah, it was. No, but even Riemann was quite advanced because usually this advanced saddle point technique is attributed to not Kelvin, the guy Stokes, because Stokes in the Stokes phenomena studied this thing, study of rainbows and this thing, studied that. But it's actually initiated by Riemann. It was noticed that it was in his notebooks that, yeah, but he never published it. But then it was discovered by Siegel, as I said, in 1932. So it was. So that's one method, but that's a very, very low key. Right now considered very low key. There are much more advanced methods, which I'm not sure. You have to ask Oldishko. Oldishko, the guy who calculated these zeros.
Oh.
Yeah, and Montgomery. Yeah.
Well,
No, I think he just came up with the conjecture. Oldishko Oldishko, I think, wrote a paper called what is the paper called? The first 1 million zeros of zeta or something.
yeah.
Something like that. Yeah. So okay, this is the first 100, and these numbers they go on, as far as we know. So I believe there are some records. I wrote it down. I believe up to 10 to the 23 zeros have been calculated. They are all on the critical line. So it's kind of hard to imagine that this is going to go wrong. I mean, somehow a zero way up there appears. It's just so strange. And that number, that zero, is in the order of 9.04 times 10 to the power 30. That number. I think that's the record, at least up to a few years, but who knows what the record is today? I don't know, because people are just working on these things all the time. So I don't know. So yeah, experimentally has been verified that the Riemann hypothesis is actually correct up to billions of zeros, but who knows? No, this is really something.
There's somewhere that there are some number theories to reservations about it.
Oh,
Because the theory, as we've seen, lots of log.
yes.
These terms very late. It's like multiple convolutions of log
Oh,
change later on.
I see. I see.
But like,
Yeah, I mean that's really amazing. I mean something. It's just yeah. I mean it's true up to all those heights, and then boom, something goes wrong. It's very strange. I mean, primes are the strangest things, yeah. Yeah. Any other questions or comments, guys? Yeah. Mike. Yeah. Yeah, but the asymptotics was found, yeah. T log T, essentially, minus T. You can remember that is of the form T log T minus T, yeah. Yeah.
So I guess the question I'm just going with that. So a certain all zero.
No, no, but definitely you know that there are these many zeros for sure. But do we know exact? No.
Right. So you know,
And do we know if they're by this formula, if they are on the critical line? Absolutely not, of course.
it's not a list of things that also some.
Yeah. Oh, you mean up to 10 to the power? No, no. The first series, the first 10 to the power 23 zeros consecutively computed, and they are all on the critical line. They're on the critical, yeah. And then, yeah, indeed, what you say is there is something there, indeed, that there are some blocks of zeros that appear after this limit, and they are also on the critical line, but we don't know what happens between them and this limit. Yeah, so there are some gaps that are we don't know, but then there are some bigger limits blocks that are correct. Yeah, there are all kinds of things about this. Just like Hardy, I don't know. Did Hardy prove that 40% or of zeros are on the critical line or something? There are statements like this. Yeah. Sorry.
Then they help all the zeros.
I don't know how they calculate it though. Don't ask me.
But the part is all exactly 1/2.
No, it's half. No, that's half. Yeah. Yeah, that's half. That's not approximation. Yeah. The approximation is in the imaginary part. No, that's always on the critical line. Otherwise, we wouldn't know. Yeah. That's why, indeed, that's why we don't. I mean, you cannot totally use computers to do. There is some deep analysis going on to make sure that at least the real part is on the s equal to half. But yeah. Any other questions? Can we move on then? So the last thing I wanted to say, and then we leave this zeta function for now, is actually, so let me write it down. So this is like Riemann's first proof of analytic continuation. So remember that the proof that I gave, it was his second proof. We started with writing lambda to the power minus s, right? Remember we started with this formula equal to 1 over gamma s, right? Integral from 0 to infinity e to the power minus lambda t to the s over t dt, right? And then if you put lambda, so this was true for all lambda positive. And if you put lambda equal to n, you get n to the power minus s equal to 1 over gamma s integral 0 to infinity e to the minus nt t to the s over t dt, right? And then so this is for all n equal to 1, 2, so on. And if you add these things on the left-hand side and right-hand side, you get sum. So it follows that zeta, which is sum 1 over n to the s, is equal to 1 over gamma of s, integral 0 to infinity, a sum, now e to the minus nt, and from 1 to infinity, right? N to the 1 to infinity, t to the s over t dt. So this is the steps that we took in our derivation of things. Then at this point, it's like you're in the woods, and then there is a fork. There are two roads itself, this or that. So this we took ended up with theta function, right? So how did we ended up with theta function, by the way? What move we did in order to get theta functions? Remember? I mean, what was Riemann's strategy to relate this sum to theta function? What is theta function? Do you remember? Yeah, the theta function should be you have to put it into small chips and put it in your brain. Theta function. It's like e to the x. You should think of it like e to the x. That's as important. So theta of t is equal to sum e to the minus pi n squared t, and n belongs to z, right? So Riemann knew about this, and he said, okay, I'm going to take n to be n squared, and you're summing over n squared, and then we went through that. Okay, so that's the first method. I mean, sorry, second method. Yes. But the first method, actually, he said that, okay, well, this is geometric series. I can sum it. There is a geometric series here, right? I mean, what is the geometric series? What is the sum of this? E to the minus nt, and from 1 to infinity. That's, of course, e to the minus t, 1 minus e to the minus t. And if you multiply, you're going to get 1 over e to the t minus 1, right? Okay. That's that. 1 over e to the minus. So then you can write this zeta of s simply as 1 over gamma of s, integral from 0 to infinity. So now let me write it. 1 over e to the t minus 1, as we have over there. T to the s over t dt. Yes. And of course, this is true for real part of s bigger than 1, right? Because this function is defined originally only for real part of s bigger than 1. We have no right to use this formula here. Sum of 1 over n to the s for real part of s, anything bigger than 1. And this one for now also, then as a result, real part of s has to be, yeah. Okay, then again, he uses complex analysis and he changes the integration contour. You see, now we have here over 0 up to infinity, right? So then he takes and he changes this contour. He says that, okay, I'm going to take a contour like this. So you start from infinity, you go around 0 and go to infinity. This is a contour. And it closes at infinity. And then what you say, you just say that, well, zeta of s is equal to integral. So I think he writes infinite to infinite minus So I'm going to switch from t to x. That's much more convenient. Minus x to the power s over e to the x minus 1 dx over x. Huh?
Oh, sorry.
It's over there.
And then gamma, well, gamma.
Yes, I should have gamma over there. Now, you have to be careful about the meaning of the integration. So, and this thing and why this is true, because that's kind of funny. So let me just write the definition of this minus x to the power s is exponential of s log of minus x. Now, this is, you have to think about it. This is not obvious that this integral from 0 to here is equal to this integral. This is not obvious. But if you think about in terms of this formula and the value of this, and for example, yeah, I mean, so I just put it here and ask question why. This is something that you should be able to decipher and to handle using your complex analysis, basic complex analysis things. So I won't talk about that more, but then I just write this. I can imagine this is coming from like up to delta here. So then you can divide the integration into two pieces. So let me write it. So what he does is that he says that, okay, integral plus infinity to plus infinity is equal to integral from infinite to delta is this piece up there, plus integral from integral over absolute value of x equal to delta. It's this one. It's not all the circle, but I have written all the circle, but that doesn't matter because you can let delta go to 0, then it becomes really all the circle. So that's okay in the limit. Plus integral from now obviously delta to infinity back again. So he shows that, and you can do it. The middle integral goes to 0. This goes to 0. You can goes to 0 as delta goes to 0. So then he obtains a formula which is like this. Integral from infinite to infinite is equal to limit of delta goes to 0, integral from minus infinity, from infinite to delta, exponential of s log of x minus ip over e to the x minus 1 times x, and then plus another term, yeah, delta, okay, infinite to delta up there, and then delta to infinite, exponential of s log x plus ip over exponential of x minus 1 times x. I mean, I should put dx here. Is it dx over x or no, dx over x is here already. Okay, this is dx, yeah. Okay, so what you have done to this, you have added and subtracted these two terms, minus ip and plus ip. So nothing changes. You have added and subtracted these two things. But the effect of this is that this comes out to be, I want to keep the picture here. This becomes equal to e to the IPS minus e to the minus IPS. This is all in his paper, from 0 to infinity. X to the s minus 1 over e to the x minus 1. Yes. Yeah, in particular, then, so what it shows now is that integral from infinite to plus infinite minus x to the power s over e to the x minus 1 dx over x is equal to, well, this quantity we can compute. This is in terms of sign, right? E to the ix is what? Cosine x plus I sine of x, and substitute, you get, you write it in terms of sign, then this becomes sine of ps okay, gamma of s zeta of s. So this is the formula. Two I, there should be two I. Yeah. You meant two I, not two. Yeah, two I, yeah. It should be two I, yeah. So basically, then what it shows is the following kind of formula it derives. That sum of 1 over n to the s, n from 1 to infinity. This was the original definition of zeta, is equal to gamma of 1 minus s over 2 pi I integral plus infinity minus x to the power s e to the x minus 1 dx over x. Yes. Now, to go from there to the, yeah. No, sine of pi s, sorry. Sine of pi would be 0. Would kill the joy if it was sine of pi, right? Yeah, so it's sine of pi s, definitely. Now, one thing here is worth paying attention. Why could I change this product to this one? That was the reflection formula for gamma function, which was what? Remember gamma of, even I remember this now, gamma of s times gamma of 1 minus s. Huh? Was it? Gamma of 1 minus s equal to what? Pi over sine of pi s, right? So using that, you get this.
Pi.
No, it's pi. Yeah, it's pi. Okay, so now, but now here is the magic. Now, if you think about this formula, this is quite a magical formula. Why? You see, left-hand side is only defined for real part of s bigger than 1, obviously. But the right-hand side is defined for all s. You see, right-hand side is defined, but so here is the surprise now. Right-hand side is defined for all s belonging to C. Can you tell me why is it defined for all s belonging to C? Yes. Sorry?
Okay, for those values of S here.
Gamma is okay, exactly. So we have to, okay, so, well, yeah, okay, s equal to 1, there's a problem for that because it would lead to, and then these negative integers also we have to be, but I will handle, I will elaborate more on this, why I say this. But what about other points? Why is it okay on other points? Anything except gamma function, why is it okay? This is an integral. You have to worry about this convergence. Where is the problem, possible problem? No, 0 is okay. 0 is okay for this integral because you see, we are avoiding 0. We are going like that. This is the contour. 0 is avoided. So the only possibility is infinity. Why infinity is okay? This doesn't cause any problem. Yeah, this is like a polynomial of order s. Whatever this damn s is, doesn't matter. It's just a polynomial of power s, of order s. But this is exponential decay. So that's really fast convergent integral. So this is defined for, I mean, the integral, okay, so integral, let me put it like this, is defined for all s belonging to C. So where are we now? What does it mean? It means that this zeta function has an analytic continuation to all complex points, except possibly those that are poles of gamma. But those poles of gamma also you can handle, and you show that actually all of them are taken care of, except s equal to 1. I mean, we are talking about poles of 1 minus s. That's the only problem, and that's this you cannot do anything about it because that blows up at 1 anyhow. The other ones are all okay, and this is the formula. And that's his first formula. So it's like amazing, right? I mean, you had something which was quite badly presented to us, but this is like much better presentation. And you see that. Can you give me an example of this in much more elementary terms of analytic continuations where you have something which is not easily decidable if it is analytic, can be analytic continuous or not, but then you do something to it and then it becomes continuable. There is such a word in English, continuable. Can you give me an example in a much more elementary level? This, I'm saying this happens all the time. This is nothing special. I mean, the thing is special, but the method is universal. Give me an example of a function which in its original form is not clear that can be analytically continued. But when you give a different formula for it, huh? What like
the game of factorial is not clear, you can extend it, but if you write it.
Oh, but yeah, but that's that even is not defined on some domain. That's like on some integers, but so no, that's not what I have in mind. Oh. Yeah, but I mean, okay, so that also comes into in another context becomes relevant. What you say exactly, but just a simple example. I'll give you $1. I'm not going to go $100 this time for sure. Yes. Huh?
Z R S.
Z to the power S. But that's Z to the power S. So which one is the variable? Is Z constant or S constant, or which one?
See, fix Z complex constant.
Z. But this can be handled by exponential, writing it instead of exponential and this sort of thing. That's not. Huh? Log, something much simpler. I want something simple. Log scares me actually. I'm really afraid of log. I don't know if you are, but I'm really, because it's not a function. It's a different type of beast. I mean, log is not a function. Yeah, all of this. Oh my God, I have to handle with this. Who goes into covering universal, covering all this? No, I'll give you an example. What about this? 1 plus x2 plus x3 plus x4. Imagine someone gives you this function and you didn't know what this function is. Or, I mean, okay, well, we know that this is convergent for absolute value of x less than 1, and it's divergent for absolute value of x bigger than 1, right? Divergent. And for absolute value of x equal to 1, is it convergent or divergent? Conditionally convergent at x equal to -1? This function? No. The general term of this doesn't go to 0 if absolute value of x is 1, right? So it's divergent here and divergent here, but absolutely convergent over there. So someone asks you, does it have analytic continuation? Does it? Yes, it's equal to 1 over 1 minus x, right? Because you have a second formula for it, which is equal to 1 over 1 minus x. So it actually can be continued magically to the whole complex plane except s equal to 1. But if you didn't have this geometric series formula, you wouldn't be able to make this statement, right? Because by looking at it, you don't know. So I'm going to test you. Imagine someone puts something like this: 1 plus 2x plus 3 squared x2 plus 4x squared x3 and so on. You put some damn coefficients over there, still is convergent absolutely for absolute value of x less than 1. Can you tell me if it has analytic continuation or not? So no, you can't. I mean, if you give me an answer, I will modify this by another thing, which is kind of, so it's just you're going to lose no matter what, because this analytic continuation business is a very, very nasty business. And anytime you want to do analytic continuation, you have to find another formulation for the problem, and that's actually what Riemann says. In the paper, he says that I'm going to give another presentation, which is manifestly defined for all complex numbers, and then that. You guys, I think it's enough for now because I don't want to force everything just to finish right now. So let's finish now, and then okay, and then we just maybe a little bit left over. I will do it on Monday. Okay, yeah, it's stopped. What recording?
Tuesday.
I'm sorry, Tuesday. Yeah. But I'm gonna.